capabilities model capture comes in triggers?
I mean, it's just, the idea is somewhat similar. Capability model, also strongly limits what you can do. And this is, in a certain sense, it's a little bit more like an access control list, since the kernel, there aren't capabilities in a little table somewhere. The kernel kind of has a list. It knows who you are, and it's got a list of what you can do. But so they're kind of, access control lists and capabilities are sort of equivalent to each other. It's a different way of doing it, but it's similar in spirit, although it's a little bit different implementation.
Can you comment on why rings haven't been used, even though we have 4 of them?
Windows didn't use it, and Unix didn't use it, so they just, legacy. It was just, Multics used it. But, Unix, came from Multics, but it went through a path where the PDP-7 didn't have 4 rings, and the PDP-11 didn't have 4 rings, so they lost that, along the way. Multics actually did use the rings. And so just legacy. Windows doesn't do it, Unix doesn't do it, and so people don't do it. Also, that's one of the things where I'd say it's probably a bad idea, because if you're tying yourself to a system which requires 4 rings, and you move to something like the ARM or the MIPS or something which doesn't have 4 rings, then you're hung. And you can sort of count on a kernel mode and user mode. You can't count on 4 rings on other architectures. So my inclination is it's actually a bad idea because you're tying to something that's a little bit too architecture specific, and you might regret it later.
How influenced were you by the design of Unix?
Excuse me?
How influenced were you by the design of Unix?
I mean, we're certainly aware of it, but I never had the source code, and other than the fact that we knew it existed, basically not very much. I mean, but this is open source, and but that's been around for. Sometimes I get into arguments with people about microkernels. Say microkernels, bad idea, and I said, well, I think QNX actually sort of dominates the embedded space. It's a microkernel. It has some of these features, not all of them, but some of them, and it's very, it's used all over the place. But you just know, I don't have one on my desktop. Well, there's more to the world than your desktop. But yeah, it's certainly somewhat like QNX. But this is an open source system where you can play with the source. The servers, like the file server knows the POSIX calls. So the file server gets a POSIX call, and it's got to translate it into whatever needs to be done at a lower level to make that happen. So the calls that the user makes are basically all messages to the file system or the memory manager or somebody, and there's a library routine called read in the library. So that's, if you call read, it'll be linked into your program, and read knows what it's supposed to do. It's supposed to send a message to the file server, and not the memory manager, and not the process server, the file server. So it makes a message formatted in a certain way with the parameters sent to the file server, and the file server knows how to carry out reads and sends it back. So there's little stubs basically in the library for read and fork and so on. Fork knows it's supposed to talk to the memory manager or the process manager, okay? And so every POSIX call knows which of the servers it's supposed to talk to. It makes a call to that server, sending it the parameters, and that server knows how to do the work and sends the answer back. So there's 2 levels of sort of system calls. There's the POSIX level, which is implemented by library calls to the servers, and there's the actual kernel functionality, which the servers use to get their work done. And those are things like managing interrupts and very low-level stuff. So there's 2 separate levels in there. And the top level is the NetBSD sort of format POSIX. The bottom level is our proprietary kernel interface.
But then when I fork, for example, the file server needs to know that the new process also has the same.
They got to talk to each other, right? So the file, if you're forking, the process server has to tell the file server and the kernel, hey, I made a new process, and this is where it is, and its parameters. So they talk to each other. Absolutely, absolutely. I mean, we never, our focus, and given we had like 4 programmers, so it was limited manpower, we never really looked much at performance. The thing which, last few years has told me performance is not important is that there's a lot of Android phones in the world, okay? Android uses Java, which is interpreted, okay? If you can live with an interpreted computer, then don't tell me important, you lose a factor of 20 there. Don't argue about 50% if you can live with a factor of 20. No, but I know the L4 guys, in Dresden, they made a lot. They really tried to get the performance of L4 really, really good. They made a big effort, and it's also a microkernel, and they got it down to about 5%. They could run Linux as an application program in user space and it was only 5% slower than Linux on the same bare hardware. If they could get it down to 5%, we could probably get it down to 25%. I mean, we're not, the kernel wasn't designed for high performance. But, you know, I would say if you can live with a factor of 20 by running things in Java, you know, 25% probably is not, you know, fatal except in some very specialized applications. But even in real time, the processors are so fast now, you need an awful lot of, you know, a very, very critical kind of thing where you can't live with, you know, a little bit of loss because the CPUs are so fast. But it hasn't really, we haven't really measured it much.
You talked about the recovery mechanism with the Mongo process that restarts some of the servers, and you also talked about a live upgrade. Why didn't you use the regular server replacement process as the mechanism for the live upgrade?
The problem is you have to remove the state. If the process that you're replacing, like the file system, has a lot of state, you got to move that state over. And moving the state over is very complicated. And that's the whole story.
When you restart the server, doesn't it start with a fresh state anyway?
It starts with fresh state, but if you want to have Apache up there, you know, still use the file descriptors it's using.
Oh, okay. So
You
when
know.
you replace the server, anybody that had a partially completed state.
I mean, if an application program's going to open files, you better keep all the inodes and file descriptor information in the new one, and the transfer of that state is the hard part.
But then how do you keep it when you restart the old one under a crash situation? The disk driver locks up. How do you keep it so that Apache?
The drivers generally don't have much state, and the users of the drivers have to be written in such a way as they have state. So when a file system calls a driver, it can't just say, do this and forget what it was doing. It has to keep in its own memory the fact that it asked somebody to do it, do a read from this block and so on. So in the event that the driver answers, I died, it has enough information to ask the new guy to do the same thing. So the users of these things have to be basically idempotent. So of course, some restrictions on how the servers are written. So in the case a driver dies, they have the information in their own memory to, you know, restart it. But that isn't hard to do because the way you communicate is sending in a message. So what you do is you keep copying the message. Don't just throw it away.
But I guess the question is, what if one of these stateful things, like a file system, needs to be restarted by the reincarnation?
I say we're still working on that. We have some ideas how to do that. We're working on very high-speed checkpointing, so we can do a checkpoint. You know, the loop is get request, process request, you know, send answer. All the servers, all the drivers and servers have this structure. Okay, they're all sort of message-driven, and once every time around, we have a very, very fast way of checkpointing everything, so we can make a checkpoint of what's changed since last time, so that we can restore it. But that's not in the current code, and may or may not ever make it in there. So by doing very high-speed checkpointing, we can restore the state if we have to, but that's not in the current release.
Amoeba comes to mind when you talk about this. How much of this is an evolution of that?
Not really none. Amoeba was never really POSIX compatible. It was designed to be really, really, really fast, but it was not aimed, you know, it had its own interface. It was all capability based. It was completely different architecture. Anybody else here? Okay.
The kernel being the size that it is, it's getting sort of in the realm where you could start attacking with formal methods. Have you sort of done any of that?
We don't have the manpower. I mean, the L4 guys actually proved the L4 kernel to be correct. And their kernel is also in this order of magnitude. But it took them 20 man-years to do it. And so we don't have 20 man-years. But the L4 guys showed you could do it. You know, so we didn't, but somebody else could.
Could you do multiprocessors?
It's not in the current release, but one of the PhD students did a multi-core version where he got some of it, like the TCP/IP stack, running with TCP on one core and the IP on another core and the firewall on another core and the Ethernet driver on another core, and they all worked together nicely. But that was, you know, his PhD thesis, and he showed it could be done, and it had some nice properties, but it didn't make it into the main line. But one of the things I discovered was that doing a product development and doing PhD research don't always work together. The programmers were really focused on high quality. They tested all their stuff. They wanted it to work even when they weren't physically in the room. The PhD students didn't have any of this. You know, if it worked for them while they were there, that was good enough. And it's hard to merge those. I've written, some of you may know, I wrote an article called Lessons from 30 Years of Minix, which I've submitted to CACM, and it's been reviewed, and I think it's likely to be accepted, but we're not quite there yet. There's a few changes they wanted, but I'll make the changes. So there's a fair chance it'll be in CACM sometime later in the year about some of this stuff.
Back instances of microkernel, or did you have one microkernel run and manage all?
The microkernel is so small, I'm not worried about faults in it because it's fairly stable. But the thing we're looking at the multi-core is better performance in the sense of if the file server runs on one core and the virtual file server runs on another core and memory manager on the third core, and they're always hot. And whenever now you switch from somebody sends a message, it goes to the kernel, you do context switch, goes to the file system, another context switch. All those context switches hurt performance. If everything was hot and you just sent it to a thing which only ran the file system or only ran something else, then you could make the performance probably much better. And like nobody worries about RAM anymore. They just waste it like crazy. Even though when Minix first came out, everything would fit on one floppy disk. I think we're moving to a world where 64 cores is sort of the entry model, and going up from there. In which case you get cores out the gazoo, and you can afford to waste 30 cores on the operating system because the applications don't need more than 30 cores. And then you could have everything on its own core, and then very efficient message passing, and everything's hot, and you never you never screw up the branch tables or the TLBs or any of that stuff. That's sort of the direction we were looking at with the network stack.
Is there been any consideration, with regard to the last question as well, to NUMA, and also how that's going to be affecting cores, as in x86 the asynchronous hardware access
That,
is getting funky.
remember, Minix is a message passing system. It doesn't use shared memory. Okay? And so if you pass messages, that the whole NUMA, the whole issue of memory coherence, and he can read it fast and he can't read it at all, it becomes a very different thing in a message passing model. What we need is a way for A to send a message to B efficiently, and A doesn't need it anymore, and he can release it out of his address space. And depending on the underlying memory architecture, that may or may not be possible.
Well, as some of the NUMA stuff is actually expanding into asynchronous access to everything, including cores, including on a CPU, maybe 8 cores on one bus.
Yeah.
Another 4
I
on
mean,
another.
we haven't looked at some of the more exotic stuff. The thing that we want, and which some new architectures may have, is the ability to send a block of text from A to B, and then A abandons it, and now it's B only. And depending on how the memory coherence works on some of these things, that may or may not be built into the thing. That would be good for us. We don't need a lot of the shared memory things have the problem that if A writes to memory and B reads from it, he doesn't get what A wrote unless you do a barrier operation, which takes 4 minutes. And so the whole issue of memory architectures in NUMA is, kind of floating around as different manufacturers experiment with different reasonably efficient or inefficient models. Okay, I've been evicted.
Is supposed to be happening.
Okay, thank you.